In the next module, we're going to begin taking a look at NXOS programmability. So here we'll begin really taking a look at the NXOS standalone programmability, device level programmability. We'll take a look at EEM, or Embedded Event Manager. We'll take a look at embedded packet capture, which can be very useful. We've talked to how Linux containers can essentially run things like Puppet and Chef agents or clients. But we'll take a little bit more look at what are Linux containers if you happen to not be familiar with that. We'll take a look at what is the guest shell in Nexus 9K and 3K. We'll talk about briefly about NX-API, which is still something that we enable, but essentially we'll take a look at what the difference was in the original versions, 7.0, 7.1 of the Nexus 9K and 3K, from the next NX-API, which used JSON RPC to do the configuration, versus what we're now using in what we call in 7.2, which was codenamed the Camden release. And so what we're using now, which is called model-driven programmability, which is essentially a REST API, full REST API. So to begin with, let's talk about device-level programmability, and specifically Embedded Event Manager, or EEM. Now, EEM, Embedded Event Manager, is nothing new. We have had this for years in iOS. You're probably familiar with it. If you're not, you are missing out, and you really need to take a look at what this can do for you. This can offer you so much capability to react, or essentially make some sort of configuration change or do something. Doesn't even have to be a configuration change, but apply some sort of something, do something based on an event-driven subscription. So we essentially say, what is it we want to look at? And we want to look at these event detectors. Do we want to look at an event detector based on syslog? So when a syslog event happens, we trigger some sort of action. When SNMP, something happens, we trigger something. When a particular timer elapses, like for instance a cron job, if you're familiar with that is, we have even the none event detection. So if nothing happens, we can do something if nothing happens. So maybe we're expecting things to happen, and all of a sudden if nothing happens, that's when we want to act. That's when we want to have a trigger. Various hardware environment variables such as fan, temperature, fan speed, power dips below a particular voltage. We can just have a watchdog that's sitting there watching a process. Okay, we can have interface counters once they pass the certain thresholds. We have various XML remote procedure calls that can trip or trigger event detectors, CLI event detectors, OIR, ERM. Really, there's so much thing. NetFlow, IP SLA, routes can occur, CDP or LLDP, neighbor adjacency, find or lost. All of these, MAC address, 802.1x, authentication, all these can be event detectors that trigger some sort of EEM applet, which can be single or multi-event correlations to something that we do. So maybe we write something to syslog if we see something happen. We email someone, we set an SNMP counter, we do an SNMP get or a notification, we reload the switch, we perform some sort of application-specific configuration, we run an applet, CLI applet or a kind of a macro, we run some sort of a shell policy or tool command language or even Python. So that's something we'll be talking about, especially in the Nexus series. EEM can trigger Python, so we can create our own custom Python. And in fact, I talked about this earlier, and at the end of this, I'll show kind of that example, or maybe kind of in the middle, that example of that scenario that I had a customer that really needed something that didn't exist today, and in order to get the sale, they really needed our switch to be able to support this kind of function. So a feature or something that essentially wasn't there, I used EEM to trigger a Python script to come up and run in a continuous loop and make changes back and forth to configuration based on real-time runtime variables. So we'll take a look at that in a little bit. So EEM applets, So for instance, if we don't have any problem in particular, we can just have fun exploring the applets. And I would definitely play around with these quite a lot. So here's an example where we have 99 bottles of beer on a wall. So we have these various action or sequence numbers. And essentially we set a variable. So the variable is called B, and we're giving it an integer of 99. And then we're just doing a very quick while loop. So while the variable B, $B or variable V, is greater than 1, we're going to echo or put or write or print the variable, however many there are, bottles of beer on the wall. And then we're going to decrement that value by 1. And we'll say, we'll write the command, take one down, pass it around. And now, how many bottles of beer on the wall now that we've decremented 1? Okay, so at this point, if we were to essentially run the alias exec, sing that we had created for the event manager 99 Bob or bottles of beer, it would go through and run this. And the idea is that at the end, you're going to see there's no more bottles of beer on the wall. So this is something that has absolutely no real relevance in the actual iOS or NXOS device, other than just to kind of explore EEM and see what can we do with it, essentially given variables and for or while loops. So we've already mentioned all this, and then we use the alias to run it. So let's take a look at maybe something that's a little more real world, where we have a network use case and we want to monitor our memory. So the problem is that monitoring memory spikes are good, but we also want to monitor the total processor memory. So we're going to use the integration of EEM plus ERM, or event resources and resource policies, to trigger an embedded event manager event when the processor memory is greater than 80%. So we go into resource policy, we define a policy and run it or give it global access, global precedence. And within the system, we're taking a specific look at the memory or processor memory, and we're stating that we have a critical alert once the rising threshold goes above 80%, and we're going to look at it in 5-second intervals. And then we're going to use EEM, an event manager applet, give it a name, total memory check or top memory check, say the event resource policy, CRITEMEM, is what's called. So we're using ERM and we're calling it from EEM. And the action, if this happens, if the processor memory goes above 80%, then at this point we will take a particular action. This is just essentially a sequence number, and we'll use an email server to SNMP to send out an email. So another example is, for instance, the managed network use case is staying connected. So a problem might be that we're connected to a network that goes down, but it doesn't take down the local interface. And we need to be able to detect when the network is no longer capable of passing traffic and then fail over to a second interface. So we've had IP SLA or remote responder or router responder for some time, and we've had object tracking. We're also going to use the embedded event manager to essentially the IP SLA and object tracking will test the connectivity, and the EEM will cause the configuration to fail over to a redundant interface, in this case a tunnel, when the main network no longer passes traffic. So we see a couple of old-timey folks working on really old CRTs. Actually, I think this is like a compact luggable or whatever from the late 80s. Anyhow, obviously they're not happy, and there has been a loss in connectivity. So the idea is that we're going to create an IP SLA, and we're going to use ICMP echo to ping a particular IP address out a particular interface, in this case serial 00. Use IP SLA and schedule just a sequence number 1, essentially start now and run forever, and then track this event using track 1 and IP SLA 1 that we've said to determine reachability. And then when the IP SLA goes down, we want to bring the backup interface up. So the EEM event manager, we have an applet that we've just labeled WAN_down, And we have, for instance, event track 1. So first we define the IP SLA, then we use track to track that IP SLA, and now EEM is calling that track 1. So when the state of track 1 goes to down, then we're going to take some various actions. So we have and we can label these 1.0, we could label them 1.1 if we want things to be somewhat clearly sub-actions of 1.0. So we have, for instance, we're going to write a syslog message so that we've logged it forever, and it goes in our local syslog, and if we're writing it hopefully out to a remote syslog server as well, that would be seen. And specifically, we're going to say WAN network is no longer passing traffic as a double quote, so it's a string. And then we're going to pass a CLI command. We're going to go into enable mode, just in case we were in unprivileged mode or privilege 1. We'll go to privilege 15. We'll go to global config mode, with a config T. We'll drop down into the interface tunnel 0 and do a no shut. So assuming tunnel 0 is already there, already configured as possibly a GRE or possibly DMVPN or whatever type of tunnel, really doesn't matter. All we're doing is assuming that it's already there and configured, and we're also assuming it was shut down, and we're going to hear no shut it. And then write another syslog message that we successfully failed over to that tunnel interface. And then, for instance, when the WAN comes back up, have another EEM applet that, again, tracks that state. So this is essentially always running, and it's watching that track, and when the state changes to up, the WAN network has been restored. We write the syslog message, we go into privilege mode, go into config T, go into the interface tunnel, and shut it down, and then write another syslog message saying that we return the traffic to the main interface. So for instance, it goes down, EEM as the automation engine automatically reroutes over a tunnel, assuming, let's say, we had a backup internet connection, and yeah, everything is great. YouTube is great. Okay, the reasons why we're at work. So here's another example of, for instance, tracking a particular port. So here we have an EEM applet called track 118, essentially, or understandably Ethernet 118, and we're going to use track 1, again, that tracking mechanism to see if state was down. If so, we're going to write a syslog message, and then, and of course we'd probably put that in double quotes, but at any rate, we're also going to run CLI configuration. Wrote this quickly, forgot to put in the double quotes. So action, and notice, we could have 1.0 or just 1.2. Config T, go to a particular interface and shut it down. So pretty much the same thing as before. So now let's take a look, and just keep in mind, EEM can be very useful for all sorts of things. And again, I'll give that example of kicking off a Python script here in just a moment. So let's take a look at embedded packet capture. So embedded packet capture allows us to capture packets flowing either from, to, or through a given device. We can capture packets using ACLs to filter and specify the interesting traffic rather than all traffic. And we can use captured packets. They can be exported for analysis in, for instance, Wireshark or other various sniffer programs. We do have support for Cisco Express forwarding, at least in iOS devices that have this, and process switched flows we can also support. IPv4, IPv6 are all supported. Now we're mainly talking about NXOS here, but we have embedded packet capture, and it's certainly notable that it's in iOS as well, not only NXOS. So for instance, let's define a capture point. We'll use the monitor capture command, and we will specify the point. We want to capture IP-based traffic using Ceph switching, and specifically cap file. We'll talk about this file format here in a little bit, but in this case we're going to be monitoring gig 00 and both transmit and receive directions. So for instance, the protocol, important IPv4, IPv6, IP for just IPv4. Whether we're going to be doing Ceph or process switched, always better to do Ceph on devices that support that, so we're largely talking about iOS here. The capture name, so here we're calling it cap PNT, and obviously the interface and traffic direction. So then we need to define, so that was our capture point. Now we need to define a capture buffer. And here we're going to specify what the size is of the buffer, as well as the max size, and if it is circular. So here we're giving it a name, capbuff, defining what the maximum memory size is, and then what the maximum packet slice size is. So here 1518 would essentially be our MTU, and we have some room for header. Now circular, are we going to have linear, which essentially at the time the packet capture or buffer becomes full, we'll simply stop capturing traffic and not write anymore? Or circular is going to wrap back around and overwrite. So be very careful with circular. Certainly make sure that you know what it is you're doing and that you intend to overwrite the traffic. So we can optionally limit the packets captured by amount of time or duration, the number of packets, and we can even drop every nth packet or number of packets, and we can also limit the packet rate. So something like monitor capture, buffer, capbuff, limit duration to 600 seconds. So that we don't, get too many, we don't want to run it for too long, or we want it to stop even if there aren't enough packets to fill up that 512 buffer size or whatever it is we specified. So we can also optionally define an access list for filtering, and I would highly recommend that you do this almost every time. Rarely would I do this without, unless I just don't know what I'm looking for, and then I would have a very limited buffer size and a very limited duration. But I would normally use an access list to specify the type of interesting traffic that I want to limit my captures to. So here we're capturing port 80, either destination or source port 80, both. This would be a Boolean or, so if it's destination port 80 from anywhere to anywhere, source IP source port 80 to destination anywhere would also be captured, and we'll run that against our capture buffer using the access list. And then finally, we'll associate the capture point, what it is we want to monitor, with the buffer, how much we want to monitor, and the access list specifying the interesting traffic. Finally, we'll give the start command, and then if we don't want to just let it run until it's full, we can stop that as well. Now, of course, we can send this out. So we can export this information out to a TFTP server in PCAP format, so we can use Wireshark. We can also just look at it right here on the box. So show monitor capture buffer, use the capbuff or whatever we named it, and then dump it. And we can see the ASCII and the hexadecimal. Okay, or we could decode the buffer headers using EEM. So there's actually a tools.cisco.com. We can use the decode EPC headers policy in order to essentially decode this information and take a look at, in this case, IPv6, source and dest IP, source and dest MAC, and take a look and decode this information rather than having to look at the hex. Okay, we can, of course, obviously use Wireshark or some other preferable capture utility if we have one other than Wireshark that we use. I pretty much rely on Wireshark almost daily. So we can use this for a number of things like diagnosing transient problems. So for instance, periodically your network encounters maybe strange problems that cause connectivity issues or performance. You'd like to be able to look at the traffic when it's occurring, but hindsight isn't 20/20 and it doesn't allow you to go back in time and put a sniffer on the network ahead of the problem. So kind of doing things the long way, we put a sniffer on and essentially wait till there is a problem, but the sniffer captures the traffic after the problem occurred. So in this case, the solution would be to use the embedded packet capture together with EEM to create essentially an always running, what we're calling here DPR, a digital packet recorder. And we're adding logic to recognize the event that we want and then to stop the capture. So this time the result is that the capture file can be emailed to us, for instance, for analysis, or downloaded to a SFTP or TFTP or SCP for analysis at whenever is convenient for us. So for instance, We're going to set up embedded packet capture, or EPC, to use a circular buffer and essentially run forever. We're going to capture on all interfaces so that nothing gets lost. And then we could pick a specific interface if we wanted. And then we'll start the capture manually, but EEM will take care of stopping it. So here we define our capture point. We're capturing all interfaces in transmit and receive direction. We're creating a capture buffer called capbuff, giving it a size 512, the max packet size, and circular, so it just overwrites itself. Then the capture point, we're associating the cap point to the cap buff. Okay, so associating these two, and then starting that, kicking it off. And then we're going to use EEM to, once we detect a particular pattern, we're going to go ahead and stop that packet capture. So for instance, here we have, we're reacting to a particular syslog indicating that a particular system problem has occurred. So we're looking at this syslog pattern. For instance, a crypto packet was received that had a MAC verify error. We're stopping the capture. Oops. And then we are sending this as an email out to, and you could use this as a script that if you wanted to run and just kind of, modify the variables. I'm not going to go into what all of these are right now. It gets into a little bit more logic, but you could use this if you wanted, and then send this out to an email so that you actually have this. Or you could even, just quite as easily, if it was a larger packet capture, upload it to TFTP or SFTP or SCP or really anything you want. You have a lot of flexibility here. Here we're just creating an email with a MIME header and sending the email. So let's take a brief look at Linux containers. So first of all, let's define a problem. So the problem space is that we need tools and methodologies to allow customers and partners to safely build and run applications directly on our Cisco network elements. Okay? So agent and controller designs are common in today's DevOps solutions, like we talked about with Puppet and Chef. And our customers need solutions that reduce various network chatter and allow local first order analysis. So we have a kind of an extensible network spectrum of what we allow. So if we take a look at kind of on the far left of the spectrum is a very closed system, and on the very right is a completely open system. So if we take a look, for instance, kind of nearing the left is we have the ability to run native Python. This is nice. This is certainly less than closed. It is somewhat open, allowing us to actually host. And what we're talking about here is we're talking about an NXOS switch. So if we're running, let's say a Nexus 9K, a Nexus 3K, really any of the Nexus switches have the ability to run Python natively, both in the interactive mode we talked about as well as the scripted mode when we've created our .py file and we're running that, either one time manually kicking it off from command line or remotely kicking it off with something or automatically kicking it off with EEM or something like that. What is even more open would be allowing us to host our own applications, to install our own OVAs and VMs, essentially, or applications that are running on the NXOS switch. Even more open than that is a guest shell, where we give users access in the NXOS device to a kind of a sandbox environment where they can run Linux commands, but it's sandboxed off. It's quarantined. It can't affect the main operating system. And at this full open end is Bash. And we support all of these. So even today in Nexus 9K and 3K, we support what's called NXOS Open, or Open NXOS, actually, I should say, where we give you full root access to the device. You want to, obviously there's a danger there, and you can, and first of all, network admins can lock this down if they want, but we're giving you, the purchaser of the hardware, essentially the right to do what you want with that switch. You bought the switch, you can get in and if you want, you can kill all the processes. Now it would obviously kill all your routing and not be good, but you do have full access to this Bash shell. So what we're doing now is we're really empowering customers to innovate. So if we take a look at, for instance, the historical way of doing things, Cisco would deliver a network element with, a router, a switch, a network device with rich features, optimization for those features, and a secure software stack. And this is great, right? Cisco customers deploy this and manage those network elements. They deploy various business functions on those. But what happens when a Cisco customer needs a new capability? Well, what they do is they go to Cisco. They go to their sales team, their account team, their interaction with the BU, the business unit that creates that particular product, and they request a feature. Now, as they request this feature, first of all, keep in mind there's obviously a large backlog of features that have been requested, as well as things that Cisco has as initiatives to create new features. So what happens? Well, just like any other business that is public, beholden to shareholder type company, we're going to prioritize what is going to make us the most money first, right? It just goes without saying, we're not in it to be a .org, we're in it to be a .com, right? So we're going to prioritize what feature would drive the most money, the most value. So if you happen to be a customer that has 100 million Cisco devices, being a little facetious, you're going to get a pretty high priority, especially if you're going to put that on a lot of devices or need that in order to continue buying Cisco devices. If you're a small mom and pop shop or a small customer, you may not have the same level of priority unless Cisco gets enough of these aggregate of the same exact request from these commercial or small medium business space and realize that as an aggregate they can drive a good profit return on dedicating their developers to creating this feature and going through QA. Because you have to think about anytime they create a feature, it's probably going to take more than 1 or 2 developers to work on, maybe 1, probably more like a team of developers. They have to go through Q&A testing, regression testing, and this all costs money and takes time. So they have to prioritize what is going to be a profit returning. So at some point, let's say Cisco agrees and they implement this new capability. And finally, Cisco deploys this new capability to the customer, and then the customer deploys it based on a software upgrade. Okay, so this is great, but this life cycle is a pretty long life cycle. It doesn't happen overnight. So for instance, maybe we need automated management scripts, automated system visibility, automated fault detections, or proprietary business functions, things that essentially Cisco maybe hasn't yet provided, or things that are proprietary to our business and Cisco couldn't provide, really. So what if Cisco gave the customer the ability to implement their own new capability? And this is exactly what we're talking about now. So with this extensible network element technology, Cisco now empowers the customers to innovate and create their own innovation, to create their own automation, to create their own features that can then turn into immediate returns to that business. So we decouple Cisco customers' rate of innovation from Cisco software release cycles. So those kind of longer release cycles that we were talking about earlier, here with this circular line, we're now shortcutting through. So let's give an example of this, something that I created for a customer, as I've been mentioning. I actually created it to win a deal against a competitor, and it was certainly successful, so we won this deal. But it also kind of goes to show that this could just be something that a customer needs, and they could create this themselves, or they could go to a capable solution partner or Cisco partner or value-added reseller that has the ability to do this. So let's just go and cut to an example here for a moment.